Hello, my name is Julian and I will present scaling laws for conditional emergence of multilingual image captioning via generalization from translation. For training multilingual vision language models, we typically start with images and aligned annotations. In this case, we have multimodal machine translation and image captioning data. Now imagine that you are interested in training a model for captioning in a specific language, but your dataset does not contain any captioning data for that language. So you decide to add an auxiliary task, for example translation, and hope that the model generalizes. In a real-world setting, you would have a lot more tasks and it would be difficult to know if you even miss any data. But for now, we focus on the simplified example. We pass an image to the vision encoder to extract visual features. These features and a task prompt is then processed by another encoder with the goal to create task-relevant vision representations and to instruct the decoder. The decoder is a pre-trained autoregressive language model that accesses the representations by the encoder via cross-attention layers. With this configuration, we can assume that the model will correctly handle the task language pairs it has seen during training. However, it remains unclear whether the model can generalize to tasks in languages only encountered in other tasks, such as Spanish image captioning in our example, and whether the systematic generalization is a function of scale. To measure the scaling dynamics, we first construct a synthetic dataset, evaluation set, and partially pre-trained models at different scales. The dataset consists of CC12M images described by a vision language model and CC matrix translation pairs aligned to the images via contrastive models. We intentionally omit the captioning data for most languages but German and English. The evaluation set covers the tasks unseen captioning in Spanish and Chinese, both not included in the training set, seen translation in the same languages, and seen captioning in English and German. We construct models ranging from about 400 million to 11.2 billion parameters based on the encoder-decoder vision language model Florence 2 and the large language model Gamma 2. The models are combined to create 4 variants, all using the same multilingual tokenizer of Gamma 2. We train these models for 500,000 to 10 million samples and obtain 16 measurements in total. Given these measurements, we can fit a power law. Here, the cross-entropy loss on one of the evaluation sets is a function of the model size, the seen training samples, and the initial multilinguality of the partially pre-trained model on the evaluation sets. Here we see the fitted power law for all 3 different evaluation sets. The x-axis shows the model size and the y-axis shows the cross-entropy loss. We show 3 different groups. The first is the Florence 2 group with an initial multilinguality or pre-test cross-entropy loss t of about 10 visualized by the dotted line. The second group contains the larger Gamma 2 based model with an initial multilinguality of 6 and visualized by the dashed line. And finally, visualized by the solid line, a predicted group with an initial multilinguality of 3. Each group is further subdivided into sample counts seen during training, ranging from 500,000 in gray to 10 million in orange. For unseen captioning, we see that all 3 variables matter. Higher initial multilinguality leads to a large reduction in CE loss, while higher sample counts and larger models also decrease the final CE loss. Note that the 3 groups are separated due to the impact of initial multilinguality. For the seen translation task, the seen samples has the largest impact. For the other variables, the data do not provide strong evidence of an effect. For seen captioning, the model size and seen training samples predict the CE loss with initial multilinguality having only a small effect. Note that the orange lines corresponding to the same number of seen samples but different initial multilinguality move closer together if we move from the left plot with an unseen multilingual task to the right plot with seen tasks with full task coverage during training. Now that we saw that the cross-entropy loss actually decreases for unseen task language combinations, we now focus on if the model is actually able to generate text in these languages. We evaluate the model on cross-modal 3600, a multilingual image captioning dataset, with the image and the task language prompt encoded via the encoder. The blue bars indicate that the model is not able to generate captions in the correct language. However, if we add a short language-specific prefix to the decoder input, larger models are more likely to continue in the correct language. We fine-tune the models on a combined set of different downstream tasks with full task language coverage. The downstream task evaluation includes multi-thread decay translation and captioning, commute translation and disambiguation, and Cococathy and Cross-Modal 3600 captioning. For the x-axis we select the CE loss and the y-axis is the standard metric for the respective benchmark. We see that the CE loss is a useful proxy for the downstream task performance and that fine-tuning unlocks the unseen task language generation capabilities. Finally, we have a look at an example and predictions of the pre-trained 11.2 billion model with and without prefix. Here, we see an image of the Supertree Groove in Gardens by the Bay in Singapore. First, we look at the captions without a prefix. For English and German, the model is able to caption and identify the scene correctly, as expected. However, for unseen languages, the model falls back to English or sometimes German in other examples, while the language instruction is ignored. If we add a language-specific decoder prompt like the image shows, the captioning capabilities emerge for all target languages, while not explicitly trained for these task language combinations. Interestingly, there is a high level of diversity between captions in different languages, and also different hallucinations. For example, in French, the caption describes the Marina Bay Sands Hotel and fails to detect the exact scene. Thank you for your attention. If you are interested in more examples or the source code, feel free to visit our project page by scanning the QR code.